So in this video, we'll try to investigate the eddy current loss that takes place in a transformer. So in case of an eddy current loss, in order to understand that, what we take a single lamination. This is the cross section of one lamination of one means how to make you understand that it is the cross sectional area of your one lamination, and how we place those how we laminate our code, that we will discuss in some other time. So this cross section of one lamination of core, just a minute, let me try to show you that whether I can. Yes, so we are ready. Now you can see the second picture that I just have inserted in the screen area. Here you can see all these small segments. They are like means thin sheet or lamination sheet. We call them. They are the our if we draw them, it will look like for this code type transformer. I'm trying to draw it because that would be easy for me. So it would look like there's one planar sheet, one lamination sheet. Now if you pile all those lamination sheet together, they will form your core. Now here, as if we are having or we are trying to like this sheet, whatever we are having here, what we have done, we have like taking it in this way. I'm not sure whether there is any way to turn it or not. Seems there is no way that I can turn or change the orientation of this. So what is there, what I am trying to say that uh, as if let me try whether I can turn this one or not. So it is like yeah, even if I can't do this, means can't demonstrate. Let me tell you one thing. Very simple thing that here this one, all this segment, as if you have taken one of these segment here, right? This t here, if you try to find out this t, this is the thickness of one individual sheet that we have here. And then here we are having this sheet of means thickness t, and the area of that sheet is c times of t, where your t is sorry, c is greater than 1, right? So we are having our thickness, let me write it here. Obviously unit should be in length, in centimeter or millimeter, and the width of this core is, or rather width of this laminating sheet is, now c is And also we assume that the length of that lamination in this direction is 1. This is, here you can see, this is actually 1. Where is that? This is 1, right? So what is the volume? That is Ct into T. Ct square into 1. So Ct square, then the unit should be in length cube, right? Now here what we can say, uh, this direction is perpendicular, or is perpendicular to the cross section. So what is that? First, let us know that in which direction we should laminate. If you consider this transformer here, then what about your flux path? You could expect that your flux lines will flow like this. So transformer lamination should be done in a plane that is parallel to your flux path, right? We always laminate our transformer that is parallel to our flux path, whether it is transformer or it's any DC machine, AC machine, whatever machine. We do lamination to reduce the effect of eddy current. We will see how this thickness, our goal is to reduce this thickness T, but we will see that how we can reduce this T, and this T is the thickness of this laminated sheet in the perpendicular, sorry, in parallel with that laminated sheet should be placed parallel with our flux lines, right? Now why this is so, we will discuss later. Now see, and also we assume that flux is uniformly distributed. So if there is uniform distribution of the flux and it varies harmonically, now this cross section, we may consider this cross section, we can consider its build up of a set of elements. Element we are showing here. This is the set of elements, right? Where the element what we are showing here is bounded by two or means build up by means of a set of elements bounded by similar rectangles. Like we are considering a three-dimensional segment, as if like you are having just you can consider, we are considering this one lamination of this core here inside this, means the structure wise we are trying to consider a case where it is like I cannot draw it properly. Just hold it for a minute. Let me draw it. Now, there was also a slight mistake, so I have drawn it like I do not know. This is a planar 2D view of actual our 3D things. Here we are considering this cross section of that means this one is made up of set of elements bounded by similar triangles where the inner one having sides 2x and 2cx and the outer one is having sides if you add this 2cx plus dx you will have sorry it should be I made a mistake, small mistake here, where yeah, it should be cdx, so the outer one should be having it is like 2c dx here, and here also it is dx. So yeah, now it's okay. So it is like we are having the outer triangle, outer rectangle, the bigger one having side, this side is 2 of uh, sorry, c of 2c x plus dx, and this side is 2 of x plus dx, right? Now what I was trying to say by doing all this circus, that the alternation of flux within this inner triangle bounded by 2cx, a rectangle of side 2cx and 2x, will always set up EMF uh, in that elementary path, right? Because if your flux is means or flux is there, you are taking one is one segment here. So here in this elementary path will be subjected to an alternating EMF due to this flux. There is a change in flux in this. Let me shed this area so you can understand. Here it is the flow of flux is taking place, and this is also not very you should not have problem in understanding this, because see here what we have done, as if we have taken one section of this here, one portion of this, suppose this one we have taken right here. Now this one from means flux will flow through which path? Flux will flow through all this laminated sheet, right? Now this laminated sheet, now we are considering this laminated sheet are made up of elementary paths, where the one elementary path we have drawn it here with inner side is 2cx and 2x, and the outer side is 2cx plus dx. This is the outer triangle, right? So what we can expect here, that when there will be a flow of means not flow, an alteration of EMF, there will be a flux that will flow. No, sorry. Just a minute. There will be an EMF, alternating EMF induced here. Right, because this is also made up of conducting material, and because your core is made up of means whatever type of means engineered iron you take, it is after all a conductor. So this conductor is subjected to flux variation, and when there is a flux variation, there will be a flow of EMF through this conductor. Now, then this EMF will cause a flow of current. The maximum flux linked with such one element, one turn of this element is how much? That will be how much flux will be there? In one turn, the maximum flux because this is the area. See what how this is coming. This is like you have to multiply 2cx into 2x, the two sides of the inner rectangle. So you find out the maximum flux that linked with one turn of your, and then if you try to find out the total change of flux, because what we know that our EMF following this relation, so we have to find out that what is the amount of this d phi dt. Now if we try to find out this d phi dt, then what we will observe that in one cycle it is Bm 4c x square. Now there are, like in one complete cycle, it goes from 0 to 4cx square, then again 0, then again 4cx square, then 0. So total, if you try to figure out the total change of flux during a cycle is how this 16 Bm cx square is coming. If you draw the sine wave of flux, then what you will see? I am drawing the waveform for flux density. Yeah. So here it is how much? It is Bm. Now here it is how much? It is Bm. So if you see, then what is the total change during this entire duration? From 0 to Bm, that is one is from 0 to plus Bm, then there is another change Bm to minus Bm, that means 2 Bm, and again there is another change, that is means this one is due to Bm to minus Bm, then there is another change that is from minus Bm to 0. So that will give us how much? That will, this is due to this Bm, so there it is total flux density change is from 4 Bm. Now obviously you can argue that sometimes the curve is ascending, sometimes it is descending, means their slope is not same. Obviously slope is not same, but we are talking about the total change. Here we are not considering the sign. Obviously, if you try to consider the sign, you will get it will give you 0, because this change is in negative direction from plus bm to minus bm, and the other two changes are taking in positive direction. So if you average, it will give you 0. That is not an issue here. But we are talking about the total change. So the total change what we will get, it's 4 bm. So 4 bm into 4 cx square will result in this 16 bm cx square, right? Now the effective value of EMF will be, as this is a sinusoidal variation, so basically what we can say that E average is, and the total one will be this much volt. Now this RMS is acting on a elementary path. What is that elementary path? Elementary path is this one. So obviously this elementary path must have some resistance value, and how to find out? If uh, means, the element rho, if we define rho is the resistivity of the material, then we can write it rho. What is the area here? What we know, rho A by L. So in one direction the area is 4cx, and in another direction it is 4x. So here if you take one side, you will get what? Like 2cx in this direction, 2cx in this direction. So 4cx by dx plus another one will be 4x by c dx. So that gives us the specific value of, not specific value, sorry to say, that effective value of the resistance, that is 4 rho x by dx. Then here we are having c square plus 1 by c. So the EMF, we have reached the end of the paper. So let me write down the expression of EMF first. It is 8 pi root 2 ABM CX square, and then the value of effective resistance is how much. Then what is the loss? The power loss will be E square RMS by this resistance. So it will give you this much. Hmm, 8 pi square f square bm square c square x to the power 4, and then here it is 4 rho x dx c square plus 1 by c. Fine. This is the total thing we are getting here. Now another few approximation we will take. But why this is dp? This dp is because we are considering one small elementary path. This elementary path, across all this elementary path, this type of means power loss will take place. So we have to integrate from a limit from 0 to how much? T by 2. Because if your total thickness is T, where is that? If your total thickness is T, you can't reduce that the elementary one, the x cannot vary below T by 2. It is impossible. Then one side of rectangle will means try to emerge in the other side of the rectangle. So it is not possible. So what is the limit? It is from 0 to T by 2, and that you have to integrate to find out the total power. Now, based on our assumption that C is greater than 1, what we can write here, this can be approximated as 8 pi square f square bm square c square x4 divided by 4 rho x by dx. This c square plus 1 we can approximate as c, means c square, and this c square by c, then that will lead us to c, and finally here it will become c, right? And this x also will become here x cube, and this dx, this will come here. So and if we want to find out the total power, what should be the eddy current loss? If we write it like PE is equal to integration running from 0 to T by 2. Why it is T by 2 I have already discussed. dP dx. So that will lead us to a situation where it is like, sorry, not dx, dp. Obviously integration is running from 0 to t by 2, 8 pi square f square bm square 4 rho, then here it is c, integration running from 0 to t by 2 x cube dx. So finally it results as something like PE is equal to pi square 2 pi square m square bm square c. Okay, 2 also will not be there because these will result in another 4 here. So basically we will be getting something like square bm square. Here it will be 8 rho, then here it will be t to the power 4. Unfortunately there is one c. I think I have made some mistake here. So here it is squared. Okay. Now, I think I have not made any mistake, or whatever mistakes are there is corrected. So with this expression, what we can do here is that we can convert the whole thing to this row, means actually handling this CT is quite difficult. So what we can do, we can write V is equal to the volume is equal to, like we want to express it in mass by density, like in the previous case of hysteresis loss. So M by density will be T into CT into 1. If we go to the first page, you will get it. Yeah. This is T, this side is T, this side of this is CT, and this side is 1. So obviously the volume will be CT square. So if this is CT square, then what we can write that this one CT square, we can get it like PE is equal to pi square m square bm square. This CT4 we can have it like m by delta, and here it will be t square, and here 8 rho. Now this pi square by 8 rho, as rho is a property of your core material, means the resistivity of the core, so you can get it here. This total thing can further be simplified like epsilon, then it is m by delta f square bm square t square. Here this t is the thickness of the lamination. Right? So you get it. So this gives us a clear indication that this eddy current loss is actually proportional to thickness of the lamination again f square bm square, like this bm square you can visualize it like it is proportional to m square into phi square by phi square by a square. Then this whole thing can be boiled down to further. This f square phi square can be written as v square, right? Frequency into flux, that will be dimensional, that will be giving us the dimension of voltage. So eddy current loss is also proportional to voltage square. Now we'll see some of the example how to separate our hysteresis loss and eddy current loss. Like they are the two part of our iron. Now if we write here, we will consider separation of hysteresis and eddy current loss. So total iron loss is equal to PH plus E, that is M by delta, then what we can write PH plus E is equal to KH, this is F, KH F BMX plus KE F square BM square. So we have to separate them. Now most of the cases X is specified as 1.6. So in that case, how many equations do we need to find out KH and KE? We need two data set, like two different data values are required, and if X is not given, then we need three values. What are the three set of equations? Like three different voltage and frequency we have to consider, and we have to find out three different iron loss for same transformer under no load condition. We have to change the operating voltage and frequency and three times. So we will have here KH F1 BM1 X1 plus, sorry, not here. Then P2 will be So with these three equation, we have to solve it like simultaneous equation, and they will yield us this result. X is equal to, actually x calculation will lead us to the most horrible one, because x is appearing in the index term. So in order to make x appear in form of linear equation, we need to take logarithm, and I am writing the means total combined, or rather the compact expression here. X is equal to log of will be bm2 square e2 minus a square p3, where a is equal to f2 by f1. Then there will be p square minus ap3 b1 square minus a minus 1 p1 bm2 square. Here it is bm1 square, right? And here it will be log of bm2 by bm1. Now kh will be, now what about kh? Kh is equal to p2 minus a2 a square p3 f2 1 minus a bm2 x. And ke is equal to p2 minus ap3 by f2 square b2 square bm2 square into a by a minus 1. So these are the formulas that we can have for finding out the different variable or separation of hysteresis and eddy current loss. Let us take a few examples, so that will clear our understanding. Now here in this problem, what we will observe, there will be a separate variation for hysteresis loss and eddy current loss. Because hysteresis loss, let me write down the formula, then you will get it more clearly. Hysteresis loss is equal to what? pH is equal to and eddy current loss is equal to Now see, this 50 Hz transformer having equal hysteresis and eddy current losses at rated excitation is operated at 45 Hz and 90% of its rated voltage. So the rated voltage, instead of rated voltage, we are applying 0.9 V1, and also our frequency has become 0.9 of our previous rated frequency. So what we can understand that BM remains that not like this, let me write it in this way, BM remains constant. So if BM remains constant, we while investigating the effect, or rather the new value of hysteresis and eddy current loss, we can simply consider this as constant. What I am trying to say, eta, if you recall, eta, this is a means property of your material. M and delta, this actually depends on the hardness of your magnetic material. So this is a property that you have used for making of your core that alters this parameter. And M is the mass of the transformer, delta is the density. So these things, all these can be kept as constant, and as well as X. X is also your core material dependent, and BM remains constant. So this, as this BM remains constant, this whole thing, they can be written like and for this one, what we are observing, this whole thing, this T is the thickness of lamination, that is also remaining constant, or everything remains constant. What we are having here, we are having, for this particular case, it is like KF square. So if that is the case, then how can we solve it? We can solve it, it's very easily, like P8 will be at 45 Hz will be and PE new will be 0.81. Just give me a minute, there is someone is calling. So now this will become proportional to P volt. Therefore, the total reduction, if we consider, that is how much? The total reduction is actually 19%. But what about the average reduction? Average reduction, if you consider, that is means here this one is reduced by 10%, this one is reduced by 19%. So average reduction is 10 plus 19 by 2, that is 14.5%, right? So loss will be reduced by 14.5%. Now let us switch to the next problem. Just a minute. So here this problem says a single phase 10 kVA 50 Hz transformer with 1 kV primary winding draws 0.5 ampere at 50 and 55 watt at rated voltage and frequency on no load. A second transformer has a core with all its linear dimension √2 times of the corresponding dimension of the first transformer. The core material and lamination thickness are same in both transformer. The primary winding of both the transformer have the same number of turns. If a rated voltage of 2 kV at 50 Hz is applied to the transformer. First of all, this is a very interesting question. We must investigate that if we increase the dimension of a transformer by n times, all its linear dimension of a transformer by n times, then what will happen? So if you increase the dimension of the transformer n times without altering its like the other thing, the number of turn, or the, like I am trying to answer that if a 10 kVA transformer, say n, here n is root 2. So my question is that if we increase all the linear dimension by n times, then what would happen? So what can you expect? Here the things are mentioned, the primary winding of both the transformer have the same number of turns. So if it is same number of turns, then what would happen to the voltage? See, if we can recall the formula for our voltage is equal to what? It is our that famous formula 4.44 N F right. So this one, just let me just calculate once. This is actually coming from here, this root 2 into, yeah. So this is the formula. Now what happened to this phi m? Here you are actually increasing your, if you increase the linear dimension, all the linear dimension by n times, then what happened to the cross sectional area? Now if this is the previous cross sectional area, now what you are having, if this side is some value, now you are increasing this one by this. Like this is the situation here. I am taking the cross sectional area of the core that is perpendicular to the direction of the lamination. So now this is our modified area. So we can understand that area will increase by an amount of how much? It will increase by an amount of n square. So if there is an increase of n square, therefore what would happen to the flux? The phi m will become twice, in case n is equal to root 2, your phi m will become twice of the previous value, or means the initial value, right? So what we can write, or it is n square, because the cross sectional area is increased by a term n square. However, we should not forget that flux. What is the expression of flux? Flux is now, if this is the case, actually this gives you the, if you take this Ni by D, this gives you, let me show you part by part, then you will understand more clearly. If we take Ni by D, that will give us H, or the magnetic field intensity. And what we know, B is equal to mu H, and if we do phi, want to find out flux, then B is equal to phi, means phi is equal to BA, right? So from that, if we combine all of them, then it comes phi in terms of our right. This is the relation between A and I and our. Now see what we are getting here. Phi m nu by phi m old is 2. However, what about here? Mu and D, here mu will remain same, n will remain same. So our question is, the magnetizing current so what is this ratio? We know this is 2. This is I mu nu by I mu old. Here it is how much? A nu by A old, this is 2, and D nu by D old, basically this will give you root 2. So this gives us I mu is root 2 times of I mu old. So how much it will be? It will be root 2 means into 0.5, so 0.707, that is the answer. And what about the core loss? In all the previous cases, what we have done, if we go back, you can see here you can see here that your core loss, total core loss, is proportional to this. What is m by delta? This is our volume. It is proportional to volume, and also there is another term is there, that is our flux. So now that volume, if you increase, then what will happen? Your core, I mu nu we will get 0.707 ampere. And what about our power loss? Power loss will be V nu by V old sorry, I'm doing a mistake here, like volume into P old. So what is the volume? If you increase it root 2 in all directions, then it is root 2 to the power 3 into P old. So root 2 to the power 3 into 55, that will give us how much? 155.6 watt. Right? So this is the answer. Now let us move to the second question. So when you get this type of formula, first let us write what is P pH was eta by m delta, then there was some f bmx and another few things were there. Yeah, sorry. Eta f, yes, eta was there, and here it is, yeah, this formula will apply. Now this depends on the core material. This PE, that is m square bm square t square, this is the thickness, and this is also dependent on this core material, and this one is our volume of the core. Now here one thing we have to check whether what is the value of Bm or the flux, effective flux here. So what we know that if we do this, that is proportional to that, because it now see in the first case what is your V by F, it is 230 by 50, and in case of the second, if this is proportional to flux, then we will see in the second case it is how much? It is 138 by 30. So that is again will be giving us the same value, means the amount of flux is equal, means what I am trying to say, 230 by 50, this ratio is equal to 138 by 30. So that Bm is also constant. If Bm is constant, then we don't have to think about the value of x, because constant to the power something will also result in constant, and for a given material x is constant, so Bm to the power x will also result as constant. So if we can keep Bm constant, then we will lead to a very interesting formula. Then pH will solely become, if you keep all other things unchanged, right? So now you do this pH plus PE by F, then it will result to CH plus CF. So first one, how much was the power loss? In the first case, the power, yeah, where it is. Like in the first case it is 1050, and in the second case it is how much 500 watt, right? So like in one case it is 1050 by 50, by 50 is equal to CH plus CE50, and in the second case it is 500 by 30 CH plus CE30. Then from this we have to find out CH and CE. Then we can figure it out. And the same procedure we should apply for solution of that problem 2.67. What was there in 2.67? Let me share the image also. So here also you can see that they are performing this total experiment by keeping V by F ratio constant, and accordingly they are getting a constant value of hysteresis loss and eddy current loss is linearly increasing with the frequency. Now if that is the case, then we have to figure out that what is the separate value of hysteresis and eddy current loss. Here also you can think it this way, as that everything is constant, so sorry, pH is equal to CHF and P is equal to CEF square. So pH plus P by F will be CH plus CEF. So when we are talking about PCF, you can consider that this one is like P core F. So this constant part CH, that gives us how much? This is 10. So if that is 10, then what is the value of our hysteresis loss? Hysteresis loss at F is equal to how much? 25 Hz. So hysteresis loss will be 25 into 10, because CH is equal to 10. It is clearly evident from this figure. This is our CH. This is equal to 10, so it is 250 watt. So if it is 250 watt, then what about PE? Two way you can do it. Either here it is value is how much? It is, you have to find it at 25. So just multiply it. That is, what is the value here? It is 12.5. So PE would be so the value of P will be how much? Around, I think it will come 62.5 watt. So you can check by yourself. Okay.